So this is a super brief intro to polar coordinates, specifically for my students who've already seen vectors, because our book does vectors before polar for some reason. Um, so if we've got a point in the plane, like this point A in the picture, we're used to describing it in terms of its Cartesian coordinates, x, y. So this, for example, is 4, comma 3. It's up here. But polar coordinates are a very interesting and useful way to describe a point as well. And the idea is you describe a point by the distance from the origin, or in other words, the radius of a circle centered at the origin that it's on. So that's why I'm drawing this circle. And that's why it's called r for radius. So it's exactly just the hypotenuse of this triangle that we would draw all the time in trig. This is just a circle and a triangle just like always. And it's exactly like the magnitude of a vector. If you think of drawing the vector from the origin to that point, it's exactly the magnitude of the vector, nothing more nor less. Similarly, the angle at which you want to go from the origin to get to that point, that's theta. I didn't draw it in here because I'm not really happy with how Sketchpad draws those things, but theta is right here, the usual angle in the standard position, using the mathematical convention, where 0 is the positive x-axis. That's going to be another piece of data. So just like with vectors, if you tell me the magnitude of the vector and the angle, that totally tells you what the vector is. And that's the same thing with polar coordinates. If you tell me how big is the circle that my point is on and what angle it's at on the circle, you've totally specified the point. Now, how do you convert back and forth? That's one of the things you often want to do. We've been writing these formulas on the board for quite a while now, but especially in this form, we've been writing them just in the last few weeks, but thinking about vectors. But this is where we really go back to the r notation. So it's exactly what we've written. X equals r cosine theta, y equals r sine theta. That's just because cosine theta is x over r, and sine theta is y over r in this right triangle. So quick examples, if r equals 3, for example, let's do this one first. If r equals 3, slightly new circle, and theta is 30, I got it pretty close to 30 here, or pi over 6, we're often going to use radians here to be more kind of fancy mathematical. Then what are x and y going to be? X is just going to be 3 times cosine of 30 degrees, or say pi over 6, whichever you want it. Okay, and that's just going to be 3 root 3 over 2. And y is going to be 3 sine pi over 6, which is 3 halves. And if you calculate 3 root 3 over 2, it is about 2.59, and 3 halves, of course, is 1.5. It's a little off in that decimal place because this was a little off too. Okay, but it's the same idea. So notice it's exactly like converting a vector that was given in magnitude and direction form into its x and y components. Just there's nothing different in terms of the computations. Now, it gets a little trickier in other quadrants perhaps, but there's nothing different. So this is another example. If I'm over here at 225 degrees and r equals 3 still, then x is just going to be 3 times cosine. I'll do radians because in this section they do more radians. And that's minus 3 root 2 over 2. Cosine pi over 4 is a minus root 2 over 2. And y is going to be, same deal, minus 3 root 2 over 2. Turns out to be about minus 2.12 for each of them. So again, the main point is x equals r cosine theta, y equals r cosine theta, r sine theta always works in any quadrant. Now what about going backwards? Suppose I have a point where the x and y coordinates are known. So here, let's go to the simpler one first. Okay, back to this one. If you're at 4 comma 3, how do you get r and theta? Well, r is of course given by Pythagoras. This is just like taking the magnitude of a vector. Square root of x squared plus y squared. Here, with this example, r of course is going to be 5 because I set it up to be a Pythagorean triple. And then theta is the harder one. It's always true that tangent theta is y over x. You can count on that. And then of course we have the annoying thing that if you take the inverse tangent, half the time you're going to have to add 180 degrees, or pi if you're in radians. Okay, so here theta. Now we're in quadrant 1, so everything's great in quadrant 1. Here it really is just plain inverse tan of 3 over 4. I know it's tempting to take 4 over 3 because it's like this over this. You go backwards, y over x. Turns out that's 36.87 degrees. You can calculate it if you don't believe me. Okay. One last example. Got to do one in one of these quadrants, quadrant 2 or 3. Here, r, again, is 5, turns out. If you take the square root of 4.89 squared plus 1 squared. It's basically 5. I just kept the same radius. But now, if you tried to do the inverse tangent of 1 over minus 4.89, that's not going to understand that, okay? Then it's not going to give you the right thing. You're going to have to add, I'll say pi, to get the right thing in radians. So that's tricky, but it's the exact same trickiness that we had with vectors. Okay, that is our super brief intro.